So we're now going to look at rates of change. The problem of determining the tangent line to a curve and the problem of determining the velocity, or the instantaneous rate of change, of an object both involve solving the same type of limit. So the average rate of change is equivalent to finding the slope of a secant. And notice the average rate of change can be determined by the difference quotient delta y over delta x. So in our diagram here, the average rate of change will help us find the slope of the line between the points A and A plus h. So here's the point A, and here's the point A plus h. The instantaneous rate of change is the limit as delta x goes to 0. So as we bring this point in closer and closer to the point of tangency, that'll help us find what's called the instantaneous rate of change, or the slope of the tangent. So the slope of this line is equivalent to finding the instantaneous rate of change. Please note, however, the instantaneous rate of change can be found provided that the limit exists, and we're going to talk more about limits in the next few lessons. And at that point, I will describe cases where the limit or the slope of the tangent line does not exist for certain functions. So example 1. A toy rocket is launched straight up into the air so that its height s in meters at time t in seconds is given by the following equation. Determine the average velocity of the rocket between the times 1 and 4. When you're asked to solve an average rate of change question, they will usually give you two different times. So we want the average rate of change between the points 1 and 4. So we're looking for the slope of this secant line. So for this example, we want s at 4 minus s at 1, and that's divided by 4 minus 1. So if we sub 4 into our function for s at t, we get 42, and if we sub 1 into our function, we get 27. Divided by 4 minus 1, which is 3, and 42 minus 27 divided by 3 is equal to 5. So what we've now determined is the average velocity between the times of 1 second and 4 seconds. So for our average or instantaneous rate of change questions, please include your units. And that is equal to the y over the x, since the formula is delta y over delta x, and that's equal to height over time. So let's determine the velocity at t equals 1 second. So notice in this example, we are given 1 time. So therefore, we're going to look for the instantaneous rate of change. So that means we're looking for the limit as h goes to 0 of s of 1 plus h minus s at 1 all over h. So again, I would do some of this work at the side. So here's our side. And I would figure out what is s of 1 plus h minus s at 1. Because right now if I sub h into that equation, I'm going to get 0 over 0. So therefore s of 1 plus h minus s of 1, well, that's going to be negative 5, 1 plus h squared, plus 30 times 1 plus h, plus 2, and then minus s at 1, which from part A we determined that s at 1 was 27. So let's expand and simplify. So I get negative 5, 1 plus 2h plus h squared plus 30 plus 30h minus 25. And then we just keep going from there. So now we take our result here, and we're going to sub it in for s of 1 plus h minus s of 1. So we get the limit as h goes to 0 of negative 5h squared plus 20h all over h. And we know we've done this correctly because we have a common factor of h in the numerator, which will cancel the h in the denominator. So now we can cancel out the h, and we're left with the limit as h goes to 0 of negative 5 times h minus 4. If we sub 0 into this equation, we see we end up with 20 meters per second. So let's go take a look at our graph. So at 1 second, you notice here's the slope of the tangent, which is definitely much steeper than the slope of the secant. And for this slope, we got 20. And from our last example, this slope, we had 5. All right, let's conclude. So therefore, the instantaneous velocity is 20 meters per second at 1 second. And finally, our last example for this lesson. The total cost in dollars of manufacturing X calculators is given by the following formula. What is the rate of change in the total cost with respect to the number of calculators, X, being produced when X equals 100? So just to explain one more time, at 100, we're looking for this instantaneous rate of change. So the slope of this green line. So since we're looking for the instantaneous rate of change, we want the limit as h goes to 0. And for this example, it's the cost of 100 plus h minus the cost at 100, all divided by h. Since this one has a square root, I'm not going to do an aside. So this is equal to the limit as h goes to 0. So the cost of 100 plus h, if we sub that into our formula, that's 10 times the root of 100 plus h plus 1,000 minus, so if we sub 100 into the cost, we get 10 times 10 plus 1,000. So that gives us 1,100 all over h. So let's take one more step and simplify what we can. So we get the limit as h goes to 0 of 10 times the root of 100 plus h minus 100 all over h. Recall for examples such as this, we're going to multiply by a conjugate. So I'm going to multiply by 10 times 100 plus h, and all I do is change the sign between the two terms, so this will become plus 100. And don't forget to divide by the same conjugate. Next, we're going to expand the numerator and multiply the denominator. And we can see those middle terms are going to disappear. Next step, we have the limit as h goes to 0. In the numerator, we can expand this bracket here. And we end up with the following limit. The limit as h goes to 0. That's 100h over h times our conjugate. We can now cancel the h's, so this is great. That means we can now solve this limit. Now if we sub in h equals 0, you see you end up with 0.5. And this would be $0.5 per calculator. So let's conclude. So we see we have a rate of change of 50 cents per calculators when 100 calculators are produced. So two key things. Usually if you're given two x values, that means you're going to find an average rate of change. And in most cases, when you're given one x value, that means you're looking for the instantaneous rate of change. Try the following questions, and good luck.